Today's topic is resonance and formal charge. So I still need to copyright it or something, but here is my version of the equation for calculating formal charge. And why I think it's so great. You won't find this in any textbooks, but I guarantee you it will work 100% of the time for calculating formal charge. And why I think it's so great is because it's really simplistic and easier to memorize than some of the other versions that you might see in textbooks. I've eliminated the fractions completely. So when I calculate formal charge, I look up the group number of the atom, and then I subtract the lines and the dots that are directly connected to that atom. And the reason why I use the words lines and dots instead of bonds or electrons is to remind us to count those things individually. So when we're looking at shapes, the double bond and the triple bond counts as one electron group. However, when you're calculating formal charge and you have a double bond, that's going to count as two lines. Or if you have a lone pair, that's going to count as two dots. So count everything individually. What is formal charge? Formal charge is a method of counting charge, and we need to put that in quotes because this is for covalent molecules, and covalent molecules don't dissociate and they don't have real charges. So this is a theoretical charge that we're talking about here. And it's of importance because it'll allow us to figure out which structure is most stable when certain molecules have multiple possibilities. And we're going to go through plenty of examples so that you can see the relationship between resonance and formal charge. There are several rules for formal charges that will help us decide what is the best resonance structure, what's the best structure in general. And I also like these rules because they kind of allow us to check if our Lewis dot structure is correct. So for instance, this first rule here tells us that the sum of all the formal charges in a neutral molecule must equal 0. Makes sense, right? It's neutral, so we want all of those formal charges, all those internal charges, not real, right? But we want them to reflect the fact that the molecule is 0. If this can't happen, if you double check your math, you're like, I did my formal charges correctly, but my neutral molecule, all those individual charges aren't summing up to 0. What does that tell us? There's a mistake with the Lewis dot structure. Maybe you did your electron math wrong. Maybe you forgot to satisfy an octet. So this is a great check for our Lewis dot structure work. Rule B is pretty much the same as Rule A, except it deals with ions. So if it's neutral and has to add up to 0, if it's an ion, then everything that's happening internally, all those formal charges on the individual atoms, have to sum up to the overall charge on the ion. So for instance, carbonate, it's a familiar ion. Hopefully you remember that it has a charge of -2. So after you draw the structure for carbonate and assign the formal charges, those formal charges have to sum up to -2, or else the structure is not correct. Rule C is going to help us figure out what is the best structure when there's multiple possibilities. These multiple possibilities are called resonance structures. So what we want to do is create a structure that minimizes formal charge. So we don't want to have a -3 formal charge. It would be so much better to have zeros on all of those atoms instead of having a -3 and a +3. Granted, sometimes you can get those larger formal charges to sum up to 0 in a neutral molecule. But we just want to avoid them overall if we can go with smaller numbers on the individual atoms. So you'll hear me call this the minimization of formal charge. I'll say we need to minimize the formal charge. The last thing, sometimes we've done all this. They add up to 0 or the charge on the ion. We've minimized the formal charge. And at that point, we have two structures and they almost look the same. How do we decide which structure is better? So when there is a formal charge, for instance, in some of our ions, we're going to have a -1. We're going to have a +1 formal charge on at least one of our atoms because we have an overall charge. So we want to put that negative formal charge on the most electronegative atom. Makes sense, right? The electronegative atom is going to be pulling in those electrons, so more than likely it would have the negative formal charge. And that can help us decide between two very, very similar looking structures, which one is better. A and B are resonance structures. That's because they have the same connectivity. In both structures, sulfur is the central atom. The only difference between structures A and B are the location of the double and triple bonds, so where the electrons are located. In a similar manner, we can say that C and D are resonance structures. They too have the same connectivity. Boron is the central atom in both of these structures. So A and C are isomers with respect to one another. They have different connectivity, different central atoms. B and D are also isomers, or A and D. We're looking for things that have the same formula, but the atoms themselves are not connected in the same way. Let's start by assigning formal charges. So boron is in group 3, and its group number minus lines 1, 2, 3, 3 lines connected to boron, and 2 dots. So 3 minus 3 minus 2. So in this particular structure, the boron would have a formal charge of -2. Sulfur is in group 6, minus lines, so everything that's directly connected to the atom counts. 1, 2, 3, 4. We're going to subtract 4 lines, and there's no electrons around sulfur, so our dots will be 0. And 6 minus 4, I'm getting a +2 as the formal charge on sulfur. Fluorine is in group 7. Lines, just 1. And dots, 1, 2, 3, 4, 5, 6. This compound is neutral. And so it's a good thing that the formal charges add up to 0. We have a -2, a +2, and a 0. So far so good, looks good. Things I don't like, boron is electropositive. Boron doesn't really have the tendency to hog electrons, right? So what is it doing with a -2 charge, especially when it's next to sulfur and fluorine, and we know that those guys are super electronegative. So that doesn't sit that well with me, but let's continue and look at the other structures. So boron is in group 3, minus line, so I'm going to do a -2, and then a -4, since we have 2 electron pairs, 1, 2, 3, 4. 3 minus 2 minus 4, I'm getting a -3 here. Okay, not the best formal charge for boron, right? Something positive or a 0 on our boron. Sulfur, 6 minus 4 lines minus 0 dots. So we're going to have a +2 on the sulfur. And then fluorine, group 7, minus 2 lines minus 4 dots. So 7 minus 6, we'll have a +1 on the fluorine. And let me just write those in next to the atoms themselves. I especially don't like in this structure that my fluorine has a +1 charge. Fluorine, it is the most electronegative atom on the periodic table, right? So what is it doing with a +1 charge? Let's just keep on moving though and see if we came up with a better structure or a better isomer over here. Sulfur, I'll do 6 minus 2 lines minus 4 dots, and that's going to give us a 0. Boron, group number of 3 minus 3 lines minus 0 dots, that's going to give us a formal charge of 0. And then the fluorine, group number of 7, 1 line, 6 dots, we have another 0. So this is a thing of beauty here. We have 0, 0, and 0 as our formal charges. Remember, one of the rules that we just went over said we should be minimizing the formal charge. And so I really like this structure. Formal charge is so cool because up to this point, you've just had to take my word for it or the textbook's word for it that boron likes an incomplete octet. And now we kind of see why. Other things that the concept of formal charge can explain. We've harped upon the fact that the least electronegative, the most electropositive atom, the one that's best at sharing, should be your central atom. Why is that? Well, that results usually in the minimization of formal charge when you put that least electronegative atom in the middle. One last thing I've mentioned in some of the other videos is that our group 7 atoms like to be in a terminal position. And that also has to do with the minimization of formal charge. If you put fluorine in the middle of a structure like this, forget about it. You're never going to have a 0 charge, and most likely you're going to have a positive charge, which is not good for our group 7s. So everything that I've been telling you up to this point can pretty much be explained by formal charge. Last one, so sulfur, group 6 minus 1 line minus 6 dots there. We're going to have a -1 on the sulfur. Boron, group 3 minus 2 lines minus 2 dots, -1. Fluorine, we got a 7 minus 1 minus 6. So that is a 0 there. The first question on this problem asks us which structure is incorrect. And some of you were sitting there, maybe while I was talking, and you figured out that D was wrong. Because the first thing you did was check the electron math and count the number of electrons available. So sulfur has 6, boron is 3, and fluorine is 7. So you might have checked and you're like, we have 16 electrons. And if we look at structure D, 2, 4, 6, 8, 10, 12, 14, 16, 18. Somebody used too many electrons when they're putting together this structure. Maybe they didn't notice when they were like actually drawing it. Well, now that they've gone through and assigned formal charges, the mistake kind of pops out at them. Because -1 and -1 gives us a -2, and we can't have a neutral molecule sum up the sum of the formal charges be a -2. So big no-no here. The other part of this question is to justify the best structure. And hopefully at this point you're all screaming, C is the best. Because C minimizes the formal charge. Over here, as I discussed earlier, we have some pretty big formal charges. And we also have negative formal charges on things that are not so electronegative and shouldn't have negative formal charges at the end of the day. In this course, we're going to focus on resonance structures rather than isomers. So one piece of advice that I can give to you all is to draw out your skeletal structures ahead of time. So this is what I did here for the thiocyanate ion. I decided that carbon should be my central atom because it's the least electronegative of the 3 atoms in the structure. And so to avoid making the mistake of changing the connectivity, if I change the connectivity, that's going to be an isomer. So to avoid that, I lay them out, all three skeletal structures, exactly the same. I've also added double-headed arrows in between each skeletal structure. The double-headed arrow tells us that all of the structures are possible, that we're showing the different possible arrangements of electrons and that they do all occur. It's kind of like, I almost think of it as like flipping the pages of a book and looking at the different possibilities. So you need to have double-headed arrows in between your different resonance structures. I have also gone ahead and done the electron math. So for the thiocyanate ion, we have 16 electrons to work with. Let's get started. So I'm looking at sulfur right now, has 2 electrons. Let me put another 6, get it up to that octet. 2, 4, 6, 8. Nitrogen has 2. I'm giving it another 6. And I'm looking at this 2, 4, 6, 8, 10, 12, 14, 16. I only have 16 electrons and I've already used all 16 and the octet on carbon is not satisfied. So I don't have enough electrons to go the single bond route. So what I'm going to do, I'm going to erase one of these electron pairs and I'll change it into a double bond. And let me do the same thing on this side. Why not? So now sulfur has 2 lone pairs and a double bond. Nitrogen the same, 2 lone pairs and a double bond. 2, 4, 6, 8, 10, 12, 14, 16. So this structure with the double bonds uses 16 electrons. And I want to also carefully look at each atom and make sure that each atom has 8 electrons. So 2, 4, 6, 8, like the carbon is good. 2, 4, 6, 8, the nitrogen is good. Last thing, let's do square brackets with the charge on the outside since it is an ion. One of the patterns for resonance, if you want to call it that you'll notice is that when you have 2 double bonds, you can move them to one side and turn it into a triple bond. So let's do that over here. So instead of doing 2 double bonds, I'm going to do 1 triple bond. That means that sulfur currently has 6 electrons. It needs 2 more. So now it's 2, 4, 6, 8. Sulfur's good. 2, 4, 6, 8. Carbon's good. Nitrogen currently has 2 electrons. So I'll put 6 more electrons around the nitrogen. So it too has a total of 8 electrons. Now that all the octets are satisfied, I want to check my 16. 2, 4, 6, 8, 10, 12, 14, 16. So that structure also looks good. Why does the double bond have to be between sulfur and carbon? Let's do a third structure where we move the double bond to the other side. And now nitrogen has 6 electrons. We're going to give it a lone pair. Carbon is good with the triple bond and the single bond. That's 8 electrons. Sulfur needs 6 more electrons to get to its octet. 2, 4, 6, 8, 10, 12, 14, 16. This too is a good structure. So we have 3 different resonance structures. Our next task, what everybody needs to be able to do by the time they finish working with the resonance structures, is to assign formal charges and analyze which of these 3 structures is the most likely, the best of the 3. So starting over here with sulfur, it has a group number of 6, 2 lines, and 4 dots. 6 minus 2 minus 4 equals 0. Carbon, we got a group number of 4, 4 lines, 0 dots, formal charge of 0. Nitrogen, group 5, 2 lines and 4 dots. That's going to give us a -1. 0 on the sulfur, 0 on the carbon, -1 on the nitrogen. So that's exciting. we see how that these formal charges add up to the overall charge, so the -1 on that ion. Let's do the next one. Sulfur is group 6, so 6 minus 3 minus 2, we got a +1. Carbon is good, 4 minus 4, which will be 0. Nitrogen is going to be group 5, minus the lines, minus the dots. So we're looking at 5 minus 1 minus 6. We're looking at a -2 on the nitrogen. So I don't typically write this out. After a while, you'll get the hang of it, and you'll just be like, okay, group number 6, and you'll just do all this work in your head. So for instance, coming over here, we got sulfur with group number 6, and I'm like 1, 2, 3, 4, 5, 6, 7. It's got 7 things around it. 6 minus 7, that's going to give me a -1. Carbon will be 0 because it has the 4 lines around it, 4 minus 4. And nitrogen is also going to be a 0. So this adds up to -1. I never checked this middle one. Indeed, it too adds up to -1. That tells us that all of these structures are valid and all of these arrangements of electrons do occur. But the question we want the answer to is which one of these structures is most likely to occur? And let's take a step back here. Which one of these structures is least likely to occur? So that one kind of pops out at me. This is a +1 and a -2. That is not a good minimization of formal charge. These guys on the ends do much better, 0, 0, -1. So I'm going to get rid of or make a note about this middle one. This middle one does happen, but it's least likely. And the reason being, it does not minimize formal charge. I'll do FC for formal charge. So we're going to take that guy out of the running, put him in 3rd place. Now it seems like we have a tie with the other two ones because it's 0, 0, -1, -1, 0, 0. How can we tell the difference? So we're going to have to go all the way down to Rule D that says the negative formal charge should be on the most electronegative atom. The flip-flop of that is also true. If you only have a positive formal charge, that should be on the least electronegative atom, like if you had some kind of cation. Between nitrogen and sulfur, sometimes it's kind of hard to tell just using the periodic trends. So feel free to pull up a periodic table that has electronegativity values. Google electronegativity values and hit on images and you'll get a bunch of periodic tables with electronegativity values. If you do that, you'll discover that nitrogen is the 3rd most electronegative atom on the periodic table behind oxygen and fluorine. So nitrogen is more electronegative. So that means that this first structure is the most likely. And the reason being is that the negative formal charge is on the most electronegative atom. I'll do En for electronegative. This structure over here is pretty likely, but it's going to fall somewhere in between these two in terms of its probability. Sulfate, such a cool example for this topic. If I had asked you last semester during CHEM110 to draw the Lewis dot structure of sulfate, I'm very, very confident you would have put sulfur in the middle, the 4 oxygens surrounding the sulfur, and then you would have put 3 lone pairs on each oxygen to satisfy their octets. And you would have gotten full credit. Because if you go ahead and count up how many electrons you would use, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, you would have found that use the correct number of electrons according to the electron math. And all the octets are satisfied. However, this is not such a great structure for sulfate. And we can start looking at why by looking at the formal charges. So on one of these oxygens, we have a group number of 6 and 1 line and 6 dots. So that's going to give us a formal charge of -1. They all have formal charges of -1. That's not always going to be the case, but they're all connected to sulfur the same way with the 1 bond and the 3 lone pairs. So we have a whole bunch of -1s. And then for sulfur, our central atom, we have a group number of 6 minus the 4 lines, 0 dots. So we're going to have a formal charge of +2. Add up all the formal charges, you do get a -2 overall. So at that point, you're like, okay, then why don't you like this structure? Well, it does a pretty poor job of minimizing the formal charge. Let's look at the fact that sulfur can accommodate an expanded octet. It's low enough in the periodic table that it can be an exception to the octet rule. What if we double bond one of these oxygens? Just do my double-headed arrows because it is a structure. It's not wrong, but there's other possibilities. So I'm going to double bond this oxygen. Arbitrary choice there. Fill out the octets for the other oxygens. The one that's double bonded will only need 2 lone pairs or 4 electrons. And let's see. The other thing we can do, we should check that we use 32, which, counting really quickly here in my head, it is 32. Octet, 2, 4, 6, 8, 10. Again, sulfur can do an expanded octet, so that's okay. The oxidation numbers on the single bonded oxygens are still -1. 6 minus the 1 line minus the 6 dots. We're going to have -1 there. This double bonded oxygen, I'll do oxygen with the double bond, just so you know which one I'm talking about. Group number of 6, 2 lines, 4 dots. So that's going to have an oxidation number of 0. Let's do sulfur. Group number 6 minus 4 lines, group number of 6 minus 5 lines minus 0 dots. So we're looking at a formal charge of +1. Does this add up to -2? So we have -1, -1, -1. -3 plus 1 gives me the -2. So it's still a valid structure. It's still, the individual charges add up, the individual formal charges add up to the overall charge. Looks good there. And it's an improvement upon our previous example because previously we had a +2 and we got rid of one of the -1s and we brought the +2 down a bit. So can we do better? And yes, we can. So what you're going to notice is that when you double bond an oxygen, you minimize formal charge for that oxygen. So that's why in a lot of the structures you see oxygen either double bonded or serving as a central atom with single bonds on either side. So let's try that next. Let's increase the number of double bonds. Maybe that'll make things a little bit better. Now we're going to complete the octets. So this oxygen 2, 4, 6, 8. This oxygen needs 6, And of course, take a second, count all the electrons and the bonds. Make sure you only use 32 electrons. Let's analyze the formal charges to see what's going on here. The double bonded oxygen, group 6, -2, -4, 2 lines and 4 dots. So the double bonded oxygens will have a formal charge of 0. And the single bonded oxygens, 6 minus the 1 line minus the 6 dots, we're looking at -1s on the single bonded oxygens. Sulfur now is in group 6, and it has 6 lines around it and 0 dots. So sulfur now has a formal charge of 0. -1, -1 adds up to -2, but this structure is the best structure thus far. So this is going to be our winner here in terms of the most likely structure, because it does the best job at minimizing formal charge. This problem says generate at least 3 structures. So you may be wondering, why is the wording like that? And it's because it's pretty easy once we have these 3 down to generate more structures. Make some space right here. I'll do a double-headed arrow going down. So same kind of layout, except why did I put a double bond here and a double bond here? What if I put the double bond here and the double bond here? So I pretty much have the same structure. It's going to have the same formal charges. The only thing I've done is like move this double bond to this position. And if you think about all the different combinations that you could do here, you could put the double bonds here, so on and so forth. Every time you move the double bond to a different position, even if you're not seeing it as being like a hugely different thing, that is a resonant structure. In terms of who's most likely, this is going to be a tie. As will any other structures for sulfate that have 2 double bonds. So the best way to draw sulfate is to have 2 double bonds to the sulfur. There's other possibilities though that we can consider. You could move this double bond, this like mediocre or medium probability structure, you can move this double bond to each of the other oxygens and generate 3 more resonant structures right there. The other thing I've seen students do, and it's also valid, sulfur can do an expanded octet. I've seen students do 3 double bonds to the sulfur. That's another possibility. And the last possibility, even though when you start looking at formal charges, it's not very likely, I've seen students do triple bonds between the oxygen and the sulfur. So there's so many resonance structures for sulfate. It becomes almost a cool thing to look at. How many valid resonance structures can I generate for the sulfate polyatomic ion? Let's generate some resonance structures for nitrite. So right now oxygen has 2 electrons. I'll put 6 more around oxygen, and I'll do the same over here on this oxygen. Nitrogen in the middle needs 4 more electrons. All the octets look good. Let's count how many electrons we used. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We only had 18 electrons, so we used a little bit too much. I'm going to erase one of the lone pairs from nitrogen, and one of the lone pairs from oxygen. So I'm going to double bond the oxygen. It only has 2 lone pairs now. And the nitrogen in the middle has a double bond and a single bond and 1 lone pair. Octets still look good. 2, 4, 6, 8 on the oxygen. 2, 4, 6, 8 on the nitrogen. 2, 4, 6, 8 on this oxygen. Altogether, 2, 4, 6, 8, 10, 12, 14, 16, 18. So that is a valid structure. For our second structure, I'm going to keep it simple, and I'm just going to move the double bond to the other side. Yes, that's allowed. This oxygen and this oxygen are not the same oxygens. So if the electron density moves to the other side, then you're looking at a different structure. So I'll do the double bond over there, complete all of the octets, double check still that you used 18 electrons, square brackets, and we're good to go. So on this particular problem, you're like, that was too easy. Like, what's the catch here? On this particular problem, especially coming off of the sulfate problem that we just did, students might try and do, or I've seen students do this. Very creative. So 2 double bonds and 2, 4, 6, 8, 10, 12, 14, 16, 18. And they're like, I used 18 electrons and I'm going to do an expanded octet on nitrogen. It's a central atom. Let me do an expanded octet on it. This can't happen. Nitrogen's only in row 2 of the periodic table. You can only start doing expanded octets on central atoms for row 3 and lower. So not a possibility here. Make sure that your central atom is low enough in the periodic table before you do an expanded octet. Alright, in terms of formal charge, oxygen is going to be a 0. 6 minus 2 minus 4. Nitrogen, group 5, it's got 3 lines and 2 dots, so another 0. And this single bonded oxygen is going to have a formal charge of -1. So altogether, this adds up to the -1 of the ion. -1, 0, 0. Again, adds up to -1. Which structure is most likely? It's a tie. And there's no way to break that tie, because it's not like the first example where we could say, well, let's assign the negative formal charge to the most electronegative atom. They're both oxygen. We can't say one oxygen is more electronegative than the other. So my final response here will be these two structures are equally likely. So it's like probably a 50-50 split between the two.